Please get started. Okay?
So, the topic is about Columbia Space Shuttle. First of all, the Space Shuttle, here the damage, or we'll come to it later. We'll come to it later, but first the Space Shuttle is used for multiple purposes. Like, you know that the America landed humans on the moon, but it has costed many $1 million per day. And the launch vehicle was disposed of after 2 years. So, there is a need of space shuttle which can be used multiple times. So, considering the factor of fatigue, this is needed. Okay. So, the disaster happened on February 1st, 2003. It happened not during the launch by Challenger, it happened while returning. Okay. It was launched on January 16th, 2003, but this damage happened on returning. And the name of the space shuttle is STS-107, and the crew consists only 7 people. The main aim of this mission was to conduct the experiments in low gravity region, like how cell growth will affect, how lower gravity will affect the cell growth, how some animals like ants behave in low gravity. There are many of it, but because of the damage, only 40% of the experimental data is obtained. But it is mainly to conduct the scientific experiments in the low gravity region, like almost zero gravity region. Only for this STS-107, like the remaining STS missions were conducted to perform various things, but this is mainly for the scientific issues, and the 7 astronauts, the 7 crew members has lost their lives. So that is it. And yeah, carried the experiments of scientific experiments, and okay, so this is just the video of what happened while returning to the Earth. See, there is one chunk of the space, like the small parts slowly started detaching from the shuttle. So let's, first of all, let's investigate from the starting. Like, we don't know what is the cause of the failure. So what we know is there is no problem while going up. There is a problem while going from the problem while returning. So the first problem, the first abnormality occurred when the pressure sensors, like the hydraulic pressure sensors for the left wing tire has turned off. So that was the first issue. And next, these things that, as you saw that the space shuttle slowly started degrading itself. Like one piece fell from many pieces fell from the while returning. Right? So what can we get from here is like the left wing part. The parts of the left wing was not recovered yet, and the parts of the right wing was recovered. So we can say that the left wing part degraded initially. Okay, this is the first clue we have. The left wing part degraded initially, and this is the map of USA, the red areas. We will come to RCs later, but the red areas and the yellow, these are the parts of left wing. So this concludes that the initial damage in the space shuttle occurred during left wing, and next the right wing and the nozzle of the space shuttle. So first the damage occurred in the left wing. We will see what happened. As you saw, the main problem occurred while returning now, and the main issue while returning is the hot gases, because of the temperature rise due to atmospheric gases. Like here, like the plane will ascend like this, so descend like this, and the lower part of the shuttle is heated. And to protect this, like initially to protect this, we will use the ceramic tiles, which is placed using epoxy adhesive. So the ceramic tiles were placed using epoxy adhesive to the shuttle. Why we will use the ceramic tiles means it is very heat resistant and also very light. So the next flow is, this is the one of the part of ceramic tile. The space shuttle means like, the interior of the space shuttle is consisted of aluminium struts. Like interior of the space shuttle has the metal part, and the exterior which is exposed to the heat consists of the ceramic plates. And what we know from this picture is that this is the metal coating on the ceramic plate. So there is no metal outside the shuttle, but there is metal coating from this image. So what we can conclude is that the interior metal part has melted and redeposited on the ceramic plate from the left. This is made of the left collector. Okay. So also we have another flow which was neglected initially. While the takeoff itself, we observed a small debris from the. This is the foam material. Like you know that the shuttle has this huge orange tank on it. It is called fuel tank, and it is coated with foam. And this is the foam part, which due to high vibrations has left. It has broke from the fuel tank and hit the left part of the wheel. So it concludes that there is a damage occurred to the left part. It is not due to fatigue, not due to thermal fatigue or any fatigue. It is due the damage occurred due to impact toughness. So, see, this is the rocket boosters, this is the shuttle, and this is the foam fuel tank. Here, this is the part which came off from this and hit this side. And so, according to from the given dimensions, from these given dimensions, the velocity of this part which hit the left wing is some around 700 to 900 km per hour, which concludes that, which gives us the kinetic energy per meter square as 150, like around 150 joules per meter square. Okay? We will come to this picture later, but the kinetic energy of the debris which hit the left wing was around 150 joules per meter square. Now, see, this is the left wing. So, what happened was, due to impact toughness, actually, I said the shuttle, the lower part of the shuttle was covered with ceramics. And we know that ceramics has high hardness, high thermal stability, but low toughness. Right? Like, it won't show any plastic behavior. It is brittle, so it will break immediately. And people know that this would happen. The foam strikes, like the foam strikes during the launch is common. So people know that this would happen. So what people did was, especially the crucial parts like this edge of the wings and the nozzle of the shuttle, they built it with the RCC, like reinforced carbon. It is little bit tougher than the ceramic plate, but it is also a brittle material, not as tough as any metal or wood. Okay, but it is highly thermal stable. Like also outside of the space shuttle is highly thermal stable. Like the first important criteria is we need the material to be highly thermally stable. So we use RCC, but even though we use RCC, but it has like low impact toughness, like around 5 to 10 joules per meter square. but the kinetic energy of the debris was 150 joule per meter square. So the damage occurred, and there was slight opening, like slight cracks in the wing during takeoff itself. And those 16 days, like January 16 to February 3rd, like those 2 weeks around, they conducted like there was no any anomaly, so they conducted experiments, everything was fine. But while descending due to atmospheric gases, the hot air gases, as hot gas begins to fill the left wing, so the hot air gases enter the left wing. So what is inside the wing is the aluminium structure, like the shuttle is made up of aluminium crossings for the mechanical stability of the shuttle. So what happens, the temperature of hot air gases was around 1600, and we will come to it later, like what exactly happened more. But the initial, the hot air gases went inside the left wing, and we know that these are the sensors. See, this is a tire. The first sensor which was off was the tire. The first sensor which was off was this tire pressure sensor. Like it showed some anomaly in the tire pressure sensor, and eventually, like it didn't took much time. Like within seconds, like all the sensors went off, and within 2 to 3 minutes, the connection with the ground level NASA scientists went off. Like there was no connection. So next.
Okay, so I'll talk about the external fuel tank and the foam. So as we know, as Yashwanth just discussed, the foam impact was the reason for the failure of this. The foam was almost just because it was just a small suitcase, and just for reference, the space shuttle was 80 tons and 50 meters long. So we need to understand how impact is that important, because something as small as that, it just went and hit and the whole shuttle is down. So that is the spaceship, and this is the fuel cell, and the fuel tank, and this is the bipod struts. So we have something, the foam is here. But why do we have the foam? What is the point of the foam? It is because the fuel tank has fuels at a very low temperature, at cryogenic temperatures. So the foam is an insulating material over here. So that is the only purpose of foam. And so look at this. The bipod struts attached to the external wire. So this is the composition of the foam. It is a polyurethane, that is a carbonate CW1 It's a very basic structure, and the combination of factors led to the loss of. So we don't know why the left bipod strut, the left one, had broken off. We don't know the reason for that, but the foam just goes and hits the left wing. So this is what actually happened. The foam goes and hits the left wing, which basically creates a hole. And when doing reentry, it was fine during when the experiments were done, and a lot of the data was they got back pretty much 40% of the data. But then when it hits, so when on reentry is when it's exposed to the hot gases and stuff. So it goes in, the hot gases go in because the RCC composite fails, the hot gases go in, and the body is made of aluminium basically. So it goes in, and the lower part of the space shuttle is made of ceramics, and the key areas like the nose of the space shuttle is where, as you can see, it has a higher constant temperature or strain is higher than the nose, and the forward area of the left wing. So that's where we use RCC. At the bottom you can use ceramic tiles. So it hits that, and the hot air gases go in, and that's when the pressure alarms are triggered. But it's too late because it goes in, and the adhesive that holds the ceramic tiles at the bottom is melted, and so the ceramic tiles fall off, and basically the whole thing is failed. That's it for the cell. Okay, now this is RCC. RCC is a composite of carbon fibers and a carbon matrix. So as I mentioned, these are the crucial parts, the nose and this of the aluminum inside, we use a silicon carbide coating. So this is the basic structure of RCC, and this is how it looks. And tiles 7 to 14 is kind of the crucial area which experiences a lot of the temperature difference or the strains. Okay, we look at what is actually happening here.
The enhanced pictures reveal something so unlikely that no one had ever considered.
That was the foam from the fuel tank, and the phenomenon is known as impact, and as impact layer.
Yeah, so as what he said, it falls, just it's right here, it falls to the left wing and it falls impact, and whatever I explained happens after that. And this one explains where exactly the RCC styles are present and where they will.
So, music.
If it doesn't run, just explain what happens then.
Yeah, this visualization shows that this is the bottom part of the shuttle, and these are the areas where the ceramic plates are being pasted. And here the reinforced RCC, like reinforced carbon RCC is this. That's it. Yeah, see, these are the ceramic plates. Bottom of the shuttle. And this is a lot like the metallic structure for the rigidity of the shuttle. And next is the RCC, where the crucial part of the shuttle is.
Try to wrap it up in 5 minutes.
This is the temperature time curve. So our shuttle is STS1107, and this is the data of all the shuttles in the previous months. So 07, 090 are the previous shuttles. So we see this is from 44 minutes at around 300 seconds. I mean, this is the reference. You see the tail here, it was fine, and then suddenly the temperature rises. This is when the hot air gas is going. And you might ask why this is not like that. This is because the sensor stopped working basically, so it doesn't record that anymore. So we can see around this time is when the temperature rises. So this is when the hot air gas is went in. That's that. And so this is after the failure occurred. They try to see what exactly happens.
Like what happens if RCC is not there?
Yeah. So as we can see here, the relative heating rate is higher than RCC is not here. RCC is removed here. So that's fine. Yeah. So as I explained already, because the hot gas is going, it's saying when the aluminium near the leading edge is exposed to hot air, this melted the aluminium, which changes the aerodynamic properties. So now the left wing is basically off, so it loses balance, and then it topples and it crashes, it burns up, comes into the environment.
Like the phenomenon why exactly this happens is like, as I said, that the ceramic base which was pasted to the shuttle, they use the room temperature vulcanized silicon adhesive as the glue to paste the ceramic base. Initially, like heat from here cannot do any damage to the glue, like the adhesive. But the hot air gases went inside. They melted everything inside. So the glue also started melting, and the ceramic plate slowly falling off from the shuttle. So what happened is that the left side of the plane, it loses some mass, and it loses some mass, and to overcome that, they use the right wing's thrust force to balance it, and the torque created has broken the left wing. So the first part
then this is just summarizing that slide. And then again, there's no immediate catastrophic failure upon re-entry after many days is when this actually happens. And then there's something called thermal protection barrier, which is basically the RCC tiles and the RCC panels and the ceramic tiles. All of this is to protect the shuttle from the high temperatures that it encounters upon re-entry. So basically, what failed is the thermal protection barrier too. So modifications were done after this incident to make this better. So we look at that. Yeah, again, so firstly, there's something called Prof. This is a new material after the Columbia disaster, which it can withstand up to 3000 degrees Fahrenheit, and you can also reuse it unless it experiences around 2900 or higher temperatures. It's made of silica fibers and it's lightweight, and it's used at the leading edge again. Turf is process is used at as I mentioned, the nose and the front ends of the left and right wings. And so the problem was because of the foam. So later they replaced it with electric heaters, which is basically in a copper plate. We use copper here because it has high thermal conductivity. So it will distribute the heat well and it is any ice. So why ice? Because this fuel cell has cryogenic temperatures inside. So there's ice formation here, which is why we use foam to insulate it. But now because the foam failed, we start using electric heaters, which are copper based, and if there's any, it distribute heat so well that even if ice forms, it melts. And why do you want the ice to melt is it can also act like debris and impact the same story again, like how the foam incident happened. So we don't want any ice. So yeah, we use electric heaters now. And this FRCI type. It is again an aluminum borosilicate type. It has the next layer which is alpha alumina and silica fibers. It is it can withstand medium temperatures, and it is a low cost. And this HRSI type, silica.
This was used in the Columbia Space Shuttle. This one, LN900.
Right. It is heavier than FRSI. Usually, later we try to replace this with FRCI. And then, okay, so ceramic tiles, the issue is that there are way too many tiles because the tile is small, so you need way too many tiles, and that causes, at any point of time the tiles can fall off. So they engineered a kind of a ceramic insulation blanket instead of the tiles. It can withstand moderate heat, so you can't use it at the leading edges, but you can use it at let's say the parts of the aircraft which don't experience much heat. It's made of silica and glass fabrics.
Actually, just a 30 seconds not related to the materials. Actually, the initial design proposed by the NASA, before the Challenger itself, was this. So this is the fuel tank, and this is the space shuttle. But here, the space shuttle is so small, it can accommodate only crew members. But the budget, the government didn't show any budget, so it tied up with the Air Force, and the Air Force demanded that the load capacity should be large enough so that to include spy satellites, so that they can launch secretly. So if this was the initial design, then there is no chance of foam attacks, and the time taken to descend was 4 minutes, but for that was 12 minutes. So 12 minutes more time means more heat contact time. So if the NASA use this one means it can descend in low time, and the cost of production was, let's see, the wingspan is also very small compared to that one, but the load capacity is small. So this was the.
Okay, let's thank the group again. Couple of questions from the audience. Anyone? Yeah.
Will you consider the foam removal from the fuel tank as a measure of material failure, or it hitting the wingspan?
Material failure, like the foam attacks, the foam strikes was very common. We can say that it is the case of low probable case which happens.
He's asking, I think, both of them are failures. I mean, it falling off is also a failure, it hitting and our material not being able to take it is also a failure.
No, but see, we can more as the plates are the ceramics, we cannot do much about the toughness. But we can overcome the foam break-off by removing the foam and replacing it with copper.
So foam removal was a major.
Any other questions? Sanjana?
You said by takeoff there was no disaster coming. Why would it, okay, by taking off was the temperature increase?
But taking,
Won't that?
it is not as much as by coming down. By taking off, actually you are doing opposite force from the gravity. Like by coming out, the gravity is added in the heat temperature, but by taking off, there is none.
Yeah.
Also, we can say that by taking off, also like some debris might hit. Like the initial crack was small, like due to contact with many debris, like the crack increased and the disintegration.
Let me give you a hint. Try to think along these lines. What is the velocity while taking off? What is the velocity during reentry?
Yeah, velocity. Here we are giving the velocity, and there we want to reduce the velocity.
No, but what is the velocity? Do you have an idea of what the velocity is?
No, so that
Re-entry velocity compared to takeoff velocity. And where is the heating coming from? Heating is coming from what? Why is there
friction
re-entry?
forces from the atmospheric gases.
There is no atmospheric gases.
No, by coming down.
It's not atmospheric gases. Where is the heat coming? Why is it getting heated? Why does a meteorite burn?
Yeah, because of high velocity, like it enters into high velocity.
Yeah.
And because of friction,
It's called skin drag. It's a friction effect. And that drag scales as velocity squared. The amount of friction scales as velocity squared. It's all related to velocity. Anyway, go back.
You mentioned about foam as it was used as an instrument. Then you later replaced it with some conductor which I couldn't actually connect to the point how those were both of those were related. How can it use be as a replacement for foam?
No, any foam. It's an insulator, right? So electric heaters, we use electric heater to basically again as a resistance.
prevent accident.
Yeah, that's going to prevent it. Maybe ask.
Any other questions? Yeah. I can't hear you. Speak up.
Aluminum foils, yeah, but
This one,
yeah.
like it has less density and has more thermal stability compared to the previous. Like just the upgrade of this type.
Okay. I actually have no questions. Fantastic presentation. For other groups, please keep in mind that they hit everything which was required of them. I hope you are aware of the fact that they did it. They focused on the failure, they focused on the material, they outlined each of those materials.